In the deep vacuum of the cosmos, the most violent catastrophe in physics happens in silence. For a fraction of a second, a single pinpoint of light erupts with a quintillion times the luminosity of our sun, outshining the entire rest of the gamma-ray universe combined. Every day, somewhere across the sky, these invisible flashbulbs go off, occasionally blinding the detectors aboard humanity's orbital observatories. Yet every single one of these blasts occurred more than 100 million light-years away. What cosmic monsters have the power to tear space-time apart with such absolute fury? Astronomers categorize gamma-ray bursts into two distinct beasts, long and short. Long GRBs last from several seconds to minutes and mark the catastrophic death of massive stars over 30 times the mass of our sun. When their nuclear furnaces extinguish, their iron cores collapse under their own gravity into a newborn black hole. As infalling gas forms a swirling accretion disk, it unleashes twin particle jets, drilling through the dying star at 99.9% the speed of light. Short GRBs, lasting less than 2 seconds, tell an even more violent story. They are born when two city-sized, ultra-dense corpses, neutron stars or black holes, spiral into each other at fraction of light speeds. In 2017, humanity made history. Gravitational waves were detected rippling through Earth just 1.7 seconds before a short GRB flashed in the exact same direction, proving that neutron star mergers forge both black holes and heavy elements like gold. While black holes generate the most extreme bursts, astronomers uncovered another mystery: superluminous supernovae, exploding stars up to 100 times brighter than normal. For decades, scientists couldn't explain what was supercharging these blasts. Then, NASA's Fermi Gamma-Ray Space Telescope cracked the mystery by analyzing SN 2017 EGM, a monstrous explosion 440 million light-years away in galaxy NGC 3191, discovered by ESA's Gaia mission. Fermi revealed that the secret engine behind SN 2017 EGM was a newborn Magnetar, a rapidly spinning neutron star with a magnetic field 10 trillion times stronger than a refrigerator magnet, spinning hundreds of times per second. This spinning behemoth generates a Magnetar wind nebula, accelerating the electrons and positrons into high-energy gamma rays. For the first 3 months, the dense stellar debris traps these gamma rays, downshifting them into visible light and supercharging the explosion's brightness before the expanding gas finally allows the raw gamma rays to escape into space. On April 27, 2013, an explosion erupted that completely redefined high-energy astrophysics, GRB 130427A. It produced the highest energy gamma-ray photons ever detected from a burst. Within seconds of the trigger, autonomous robotic telescopes on Earth, like the RAPTOR array in Los Alamos and Hawaii, swung around in real time, capturing the changing colors of the optical flash across 4 simultaneous bands, while the explosion was actively detonating. In orbit, NASA's New Star telescope focused high-energy X-rays up to 79,000 electron volts, while Swift's UVOT instrument tracked the fading ultraviolet glow for over 10 days. Supercomputer simulations at NASA Ames showed how internal shock waves, shells of gas colliding within the jet, created million electron-volt gamma rays, while the external blast wave plowing into the interstellar medium generated billion electron-volt light. But our ability to watch the high-energy universe is fragile. NASA's Neil Gehrels Swift Observatory, which has pinpointed thousands of cosmic explosions over 2 decades, is losing altitude due to atmospheric drag. If left alone, Swift will re-enter Earth's atmosphere and burn up. To save it, NASA partnered with Catalyst Space and Northrop Grumman on a mission, launching the Robotic Link servicing spacecraft from a Pegasus XL rocket to dock with Swift in orbit and boost it back to its original altitude, giving one of history's greatest observatories a second life. When we look up at the night sky with our human eyes, the universe appears peaceful, silent, and eternal. But in the realm of gamma rays, the cosmos is a raging sea of creation and annihilation. Since its launch aboard a Delta rocket in 2008, NASA's Fermi Gamma-Ray Space Telescope has peeled back the invisible curtain, surveying the entire sky and cataloging thousands of the most extreme, energetic sources across the void. In 2017, Fermi made history by capturing a gamma-ray burst in the constellation Hydra, arriving in near-perfect lockstep with gravitational waves detected by LIGO. For the first time in human history, we both saw and heard the same cosmic cataclysm, witnessing 2 neutron stars collide, forge black holes and heavy elements, and launch relativistic jets at 99.9% the speed of light. In 2009, Fermi turned cosmic explosions into a laboratory for fundamental physics. By analyzing a short-duration burst, it proved that photons of vastly different energies travel across billions of light-years at the exact same speed, confirming Einstein's theory that the fabric of space-time remains smooth and continuous, even at the quantum edge. Looking closer to home, Fermi uncovered colossal structures towering above and below our Milky Way. Spanning 50,000 light-years, these gigantic Fermi bubbles are the remnants of a titanic eruption from our galaxy's central supermassive black hole just a few million years ago. Through machines like Fermi and Swift, we have learned that the violent deaths of stars forge the very elements in our blood, and that every flash of light across the void is a reminder of the raw, untamed power that built our universe. If you enjoyed this deep dive into space exploration and mission architecture, hit the like button, subscribe, and leave a comment below.